Good morning, my dear students. I am Dr. J.S. Sharma. I am the faculty of Mechanical Engineering teaching heat transfer at AS Engineering Academy. And this score booster session which we are trying to take up will boost up your rank and you will be in single digit ranks. Heat transfer, if you are taking it, the very first question which I am trying to take from conduction is on lagging a pipe. Generally, two particular materials are been given. One is having a thermal conductivity equal to K, other is having 2K. And there is a pipe which is carrying a hot fluid. And is asking you which particular layer should be the low thermal conductivity and which should be high thermal conductivity. The theory says low thermal conductivity material should be done inside and high thermal conductivity material should be outside. So, answer is B. But what is the support? The support is, say suppose I take a tube where I take K and 2K and here it is 2K and K, say. Assuming that the temperature inside of the surface is T1, outer is T2, in this case it is T2 and this is T1. I am assuming that temperature drop is constant in both cases as it is not specified. Hence, I will write rate of heat transfer is inversely proportional to thermal resistance. One which has high thermal resistance will try to see to it, the amount of heat loss from this hot pipe is less. So, in the first case, if I am writing it, it is two resistors. This is T1 and this is T2. I am trying to take up for this particular case. This resistance is log 2R by R, log 2 by 2 pi, inner is K, L, and this resistance is log 3R by 2R, 3 by 2, 1.5 divided by 2 pi into 2K L. So, if I am trying to compound, log 2 value is 0.693 and log 1.5 is 0.405. This is 0.693. I will take 1 by 2 pi KL common by 1 plus, in this case, log 1.5 is 0.405 divided by 2. I am getting a numerical value around, say suppose this is 0.7 and this is 0.4, say 0.7 plus 0.4 by 2. So, this resistance is almost 1 by 2 pi KL into around 0.7 plus 0.2, 0.9. If I am taking out the second situation, if I am trying to take out the second situation, this is log 2 divided by, that means high thermal conductivity material is kept inside, low thermal conductivity material is kept outside. In this particular case, 2 pi into 2K into L, this is log 1.5 by 2 pi KL. So, if I am writing it, I will take 2 pi KL common, this is log 2, 0.693 around 0.7 by 2, 0.35 plus this value is around 0.406 approximate. So, this value is approximately 1 by 2 pi KL into around 0.75. As this resistance is more, thermal resistance in this more, heat transfer in case 1 is less than heat transfer in case 2. So, the answer is material with low thermal conductivity should be used as inner layer and one with higher thermal conductivity should be used as the outer surface. There is every possibility of extending this particular question and they may ask What is the ratio of Q dot 1 by Q dot 2? Then it is thermal resistance 2 divided by thermal resistance 1. Likewise, you can straight get the value 0.75 divided by 0.9. I rate this particular question with 5 stars. Can be asked again and again. Excellent question. And at ACE Academy, we always start at 5 and reach over and above. This is the first question that we have. Second question, whenever you are going for steady state heat conduction problems, critical radius of insulation is always a question that has been sought in any pattern of examination. So, my second question, which pick that we have done it, is like a foam insulation is added to 4 centimeter outer diameter pipe. So, there is a pipe which is having an outer diameter of, this diameter is 4 centimeters. As shown in the figure, the critical radius of insulation is, he has given outside heat transfer coefficient, thermal conductivity of the foam material and thermal conductivity of the pipe. Whenever you are calculating critical radius is thermal conductivity of insulating material or thermal conductivity of that material which is exposed to the outside environment divided by heat transfer coefficient. This is watt per meter Kelvin, this is watt per meter square Kelvin, dimensionally you should get meter. So, this value becomes 0.1 divided by 2. So, this is 0.05 meters, which comes out to be 5 centimeters. Because whenever you talk about critical radius of insulation is that insulation corresponding to the outer radius of the cylinder where total thermal resistance offered is minimum. This is critical radius. Specifically for cylinders, as he has given a pipe, it is K by H naught. Question can be extended, can ask for spheres where critical radius of insulation is 2K by H naught. So, the answer is, they are really good questions. These are the questions which are always coined. Then, let's go to a question, because in steady state, apart from your basic composite slabs, asking you calculate temperature profiles at so and so locations and all, these are the questions which are selective and they are asked again and again. One such question is from internal heat generation. Internal heat generation. Let us read the question. For 3-dimensional object, he has given a 3-dimensional object. Shown in the figure below, 5 faces are insulated. That means this particular surface, say suppose 1, this surface 2, the other side, this surface 3, this surface which is at the back, this is 4, and at the bottom. These are the 5 surfaces which are insulated, and this particular surface is uninsulated one, which is PQRS. It says the 6th phase PQRS. So, I will try to see to it that this is not 4th, this is not 4th, I will take this as the 4th. So, this particular surface is exposed to a convective environment which is not insulated, interacts thermally with the ambient with a convective heat transfer coefficient of 10 watt per meter square Kelvin. So, H he has given 10 watt per meter square Kelvin. Ambient temperature is 30 degrees centigrade. T infinity is 30 degrees centigrade. Heat is uniformly generated inside the object at a rate of 100 watt per cubic meter. Whenever he is giving you the concept of internal heat generation, Q dot G is heat generated per unit volumes. So, he has given Q dot G value. This is 100 watt per cubic meter. Assuming phase PQRS to be at a uniform temperature, its steady state temperature is. So, I will say that conductive heat transfer, because of the total heat that is generated, as he is saying steady state, whatever heat that is being generated, everything has to go out. This value should be equal to convective heat transfer. So, total amount of heat that is conducted is the total amount of heat that is being generated into volume. Volume is, this is 1.5, this is 1 and this is 2. So, into volume, this volume is equal to heat transfer coefficient H into surface area that is being exposed into wall temperature minus fluid temperature. This is the balance, because at steady state, conductive flux should be equal to convective flux. Hence, I will write this as 100 into, its volume is 1 into 1.5 into 2. For clarity, I am writing it. This value is equal to, H is, he has given 10 into, surface area is the area which is uninsulated and exposed to the ambient. So, that value is 2 into 1.5. 2 into 1.5 into wall temperature minus fluid is at a temperature, ambient is at a temperature of 10, he has given you the temperature. 30 degrees centigrade. So, this is 100 into 3, 300 divided by 10 into 3, 30. 300 divided by 30 is 10. So, wall temperature is 30 plus 10, which comes out to be 40 degrees centigrade. Answer is D. Good question. This is what I am telling. The concept is asked. Mathematical complexity is reduced, and he is asking you how much amount of heat that is being generated. He is making a stabilized temperature of the wall corresponding to balance. So, steady state. Answer is clearly 40 degrees centigrade. Then, let us go to a next question. This question, I will say this is over and above 5-star. One wonderful question that is being asked till now. If you observe it, this is a question where heat transfer and refrigeration concepts or air conditioning concepts, psychometric concepts are being cloned. Let us read the question carefully. What it says, building has to be maintained at 21 degrees centigrade dry bulb temperature. So, DBT, dry bulb temperature is 21 degrees centigrade and 14.5 degrees centigrade wet bulb. Wet bulb temperature is 14.5 degrees centigrade. And the dew point under these conditions is 10.17 dpt. Dew point temperature is 10.17 degrees centigrade. Outside temperature is minus 23 degrees centigrade, T infinity naught. Internal and external surface heat transfer coefficients are 8 and 23, Hi and H0 respectively. If the building wall has a thermal conductivity of 1.2 watt per meter Kelvin, brick mostly, the minimum thickness of the wall required to prevent condensation. This is such a beautiful question. If you look at it, see, he is saying that inside you have to maintain a temperature of 21 degrees centigrade, dry bulb temperature. He is asking you what is the thickness if this heat transfer coefficient Hi is 8, H0 here is 23 watt per meter square Kelvin. If outside temperature is minus 23 degrees centigrade, given thermal conductivity of 1.2. This is the question. Now, wet bulb temperature is only indirect measurement of humidity. It is not thermodynamic state of temperature. Dry bulb temperature is the temperature that is measured by the thermometer when the air is completely dry. Wet bulb temperature is the temperature of the air which is moist air, that means moisture plus dry air, where its bulb is completely placed with a wick, and it will absorb that moisture and gives you a temperature lower than its dry bulb temperature. The difference between dry bulb and wet bulb temperature is known as wet bulb depression. If this depression value is approximately equal to 5 degrees centigrade, it is likely indication of rainfall. After rainfall, wet bulb depression is 0. So, to prevent condensation, when condensation start means when temperature of the room or the wall, temperature of the wall is less than or equal to dew point temperature, then condensation starts. So, this wall temperature here is equal to dew point, not wet bulb. Hence, this is a 3-resistor system. If you write it, it is a 3-resistor system, convective, conductive, as well as convective resistance. So, this value, if you are writing it 21, this value of temperature here is dew point 10.17. The person who has said this particular question is expecting that the student will try to use wet bulb temperature here, since there is condensations. Condensation will occur when temperature reaches dew point. So, this is minimum temperature 10.17, and then outside is minus 23. I will write the resistors now. If I write the resistors, this resistor is, see, this is a slab. In a slab, surface area outside, surface area inside, and cross section area, all three are same. So, I will take it as per square meter. This value is 1 by Hi, 1 by 8. This is L by Ka. This value is L divided by K, 1.2. This value is 1 by 23. 1 by H0 into AS0. So, how I will try to do it is, amount of heat flowing through them is same. So, I will write it as 21 minus 10.17 divided by 1 by 8. This resistance should be equal to 10.17 minus of minus 23 divided by L by K plus 1 by 23. So, this value of K is 1.2. So, you will be getting this value as, suppose, 10.83 into 8 should be equal to, that value is 33.17 divided by L by 1.2 plus 1 by 23. If you solve, you will get answer as 0.407. This is the answer. Very good question. If you are really looking at this particular question, this is giving you the which particular temperature you have to take. That means to prevent condensation inside, outside it is minus 23 degrees centigrade. It is far less than the dew point temperature of the air that is available outside. So, any amount of moisture that is present in air has already condensed, and it has reached its freezing point. Hence, you observe ice formation on outer surface. Thermal conductivity of ice is less than the thermal conductivity of water. It is less. Its value is around 0.4, 0.5 watt per meter Kelvin. Acts as an insulator again. But inside, you have to prevent condensation. To prevent condensation inside, very important, the point. To prevent condensation inside, temperature should be greater than dew point. And equality is this. If the wall temperature is less than the dew point temperature, automatically condensation starts. So, answer is 0.407. Why I am telling this particular question? Reason is, every material, everybody teaches heat. But these are the concepts where when you are going for this core booster session, you should surpass all those and reach this particular logical areas such that nothing is left out and your preparation is 100%. So, this is that question. Next, whenever you are looking at extended surfaces, this is a question from extended surface. You are looking at this question from extended surfaces. Now, if you look at this, is saying an infinitely long fin is attached to a isothermal hot surface and transfers heat at a steady rate of Q dot 1 to ambient air. If the thermal conductivity of the fin material is doubled while keeping everything else constant, is asking you the rate of steady heat transfer from the fin becomes Q dot 2, then ratio of Q dot 2 by Q dot. Whenever you are trying to look at an infinitely long fin, say this is a fin, its surface is extended, length is not defined, but generally if length is more than or equal to 5 by m, or fin factor ml value is greater than or equal to 5, then it is infinitely long fin. This is infinitely long fin. So, that is one point where you should understand. A score booster session should tell you that if length is not defined or if length is infinity, then it is an infinitely long fin, accepted. But for what is that limiting length beyond which you assume it to be a short fin means fin factor m into L value, product of m into L should be greater than or equal to 5. So, that can be another question for infinitely long. So, when you are looking at this, the rate of heat that is being dissipated by a infinitely long fin is given by under root of h into p into k into a into theta b. H into p into k into a into theta b. What is he saying? He is saying that everything else is kept constant, but only thermal conductivity is changed. I will write Q dot 2 by Q dot 1 is equal to under root of K2 by K1. And what is the relation that has been given? Everything else is kept constant. I have removed the material, replaced with a material of twice the thermal conductivity. K2 is 2 times K1, implies Q dot 2 by Q dot 1 is equal to root 2. 1.414. Answer is A. Because in the examination, you will be given mechanical engineering. Forget mechanical engineering, again you will be given heat transfer questions. And in heat transfer, you have steady, unsteady conductions, then you have convection, radiation, heat exchangers. So it is vast. Whatever question that is being given, this particular question should be attempted within 60 seconds or 90 seconds. And if it is a MCQ, it has not 2 marks. If you lose it, you lose 1/3 of its mark. So 2.667 is the ranking, is the mark of this. So it's a higher value rather than what you think. So really good questions will be asked whenever they look at specific areas. This is one question where numerically simple and conceptually more strong questions are being asked. Next, again he is saying a fin has 5 mm diameter and 100 mm long. So diameter is 5 mm. Length is 100 mm. Thermal conductivity of fin material K is 400 watt per meter Kelvin. One end of the fin is maintained at 130 degrees centigrade. So I will take base plate is 130 degrees centigrade. Remaining surface is exposed to ambient air at 30 degrees centigrade. T infinity is 30 degrees centigrade. If the convective heat transfer coefficient is 40 watt per meter square Kelvin, H is equal to 40 watt per meter square Kelvin, the heat loss from the fin is, as he has not given you the condition, basically what you have to do is you have to go with concept of correction length, right? L plus R by 2, which is equal to 100 plus its radius is 2 by 2. So 101 mm will be the length. So now the fin can be assumed to be short fin with insulated end at its tip. I will take a correction length LC, which is L plus R by 2, because this is 5 by 4. So this value becomes 101.25 or 0.10125. 1 minute. We will write this in terms of mm, later on part convert into meters. 101.25 into 10 power minus 3. He is asking you what is the heat loss. So heat loss is equal to under root of H into P into K into A into theta B into tan H of M into LC. So if you calculate M, 4H by KD, this is under root of 4 into H value is 40 divided by K value is 400 into diameter is 5 mm, 5 into 10 power minus 3. So you will be getting the value of M. LC value, if you write, this is 101.25 into 10 power minus 3 MLC is known, H value given 400, H is 40, perimeter is pi into D, pi into 0.005, thermal conductivity 400, area pi by 4 D square, theta B is 130 minus 30, 100. If you substitute, you will get answer as 5, around 5 watts. So, there is nothing much difference. You can directly take it as to be short fin with insulated end at its tip with the same length, calculate it and get the nearest value. Your answer will be around 5 watts. What I did? I calculated M. M is, first step is M is equal to under root of 4H by KD. Then I have substituted in this relation H into P into K into A into base plate minus ambient into tan H hyperbolic of M into LC. If you substitute, you will get the answer. So, this is a question where you are tested with concept and your mathematical ability to calculate it on board. So, this is one more question. Next, he is saying that a hot steel spherical ball is suddenly dipped into a low temperature oil bath. Very good. Which of the following dimensionless parameters are required to determine instantaneous center temperature of the ball using Heisler chart? Now, this was the appending of the syllabus in the recent GATE examination. Earlier, you have semi-infinite solids. Semi-infinite solids were removed and then they have added up your infinite solids with Heisler and Grober charts. If you look at Heisler chart, first let us talk about Heisler chart. Heisler chart gives temperature time history. Temperature time history at midplane or center line. And if you are looking at it, it is drawn between theta by theta c, Fourier number and Biot number. If you are looking at that chart solutions. So, if you are looking at it, answer Nusselt and Grashof, wrong. Convection it is. Reynolds number and Prandtl number, convection. Biot number and Fourier number, correct. Biot number and Fraud number, wrong. Answer is Biot, Fourier is your Heisler chart. Grober chart is drawn for theta c by theta by theta c in terms of Biot number and radial position. Grober chart only Biot number. Whereas if you are coming basically for your Heisler chart, it is Fourier number as well as your Biot. Let's come to a numerical question here. A steel ball of 10 mm diameter at 100 Kelvin, 1000 Kelvin is required to be cooled to 350 Kelvin by immersing it in a water environment at 300 Kelvin. Good, ambient. The convective heat transfer coefficient is 1000 watt per meter square Kelvin, H. Thermal conductivity of steel, K, is given 40 watt per meter Kelvin. The time constant for cooling the process is 16 seconds. Thermal time constants. The time required in seconds to reach the final temperature is, this is basically a question from transient heat conduction, lumped analysis. where Biot numbers are specifically less than or equal to 0.1. Temperature profile T minus T infinity by T naught minus T infinity e to the power of minus tau by tau star. Let us see what he has given. This is the physics behind, or the engineered physics behind the solution of the problem. Rest everything is data and substitutions. Let us see. He is saying that ambient is 300 Kelvin. Initially, it is at a temperature of 1000 Kelvin. So, it is required to be cool to 350. So, T is equal to 350. And he has given the thermal time constant tau star value as 16 seconds. He is asking you tau. So, this if you substitute, you are getting it as 350 minus 300 divided by 1000 minus 300 equal to e to the power of minus tau by tau star. So, this is 50 divided by 700. I am taking logarithm. Logarithm of 5 by 70 is negative. This is minus tau by 16. So, your time should be equal to minus 16 log 7 by 5 by 5 divided by 70. That should be the answer. That should be in seconds. Minus 16 log 5 by 70. That's the answer. And logarithmic of a fraction is negative. So, this value will get a positive value. Don't again think like, time is negative. Wrong. Or your time is equal to 16 times log 70 by 5. So many seconds. You can calculate. Then, see how beautifully the questions are asked. If you are trying to go with a subjective pattern of question, we'll be giving you rho, Cp, then all other parameters, volume. Then you would be substituting this as T minus T infinity divided by T naught minus T infinity is e to the power of minus h into As by rho v Cp into tau. This rho v Cp by h into As, which is thermal time constant, he has given it as 16. So, the examiner has made one calculation and given you, so that you will try to solve the situations. This is quenching problem. There is a quenching problem in heat treatment. You have annealing, normalizing, quenching. So, quenching problem, he has asked you what is the value. Next. Yeah. This is again highly rated question. They have asked only once. Excellent question it is. Excellent question. Let us read. Let's take time and then read this question. Two cylindrical shafts A and B at same initial temperature, T naught is same for both, are simultaneously placed in a furnace. So, if you are taking two furnaces, this is furnace A and this is furnace B, at time tau equal to 0, simultaneous means at same time they are placed. The surfaces of the shafts remain at the furnace gas temperature all the times after they are introduced into the furnace. Very good. The temperature variation in the axial direction of the shafts can be assumed to be negligible. That means the heat transfer along the axial direction is assumed to be negligible. The data related to the shafts are given below. He has given diameter of shaft 1. So, If you are writing radius of A, it is 0.2. Radius of shaft B, this is 0.1 meters. Then thermal conductivity Ka is given 40, Kb is 20. Volumetric heat capacity rho into Cp of A is 2 into 10 power 6, rho into Cp for B is 2 into 10 power 7. Is asking you temperature at the center line of shaft A reaches 400 degrees centigrade after 2 hours. That means center line temperature of shaft A after 2 hours it has reached 400. So the time required in hours for the center line of the shaft B to attain the temperature of 400 degrees centigrade is such a beautiful question given for objective. Yes, this is possible when Fourier number is constant. Fourier number is known as dimensionless time. Only number that can give me the time parameter is here Fourier number. So Fourier number is alpha tau by LC square. Fourier number for shaft A should be equal to Fourier number for shaft B. Alpha thermal diffusivity is Ka divided by rho Cp, rho into Cp, K by rho Cp, and this value for A is 40 divided by, I'll take the data, 20 into 10 power 6. So this is 2 into 10 power minus 6 thermal diffusivity. Thermal diffusivity of shaft B, if you are writing it, this is K is 20, so 20 divided by 2 into 10 to the power of 7. So this becomes 10 into 10 to the power of minus 7, 1 into 10 power minus 6 meters square per second. Diffusivity, meters square per second. So if I am writing it, alpha A into tau A divided by, this is radius, critical R by 2 basically. So it is radius of A square is alpha B into tau B divided by radius of B square. So tau B, I want time, this is alpha A by alpha B into RB by RA square into tau A. This value alpha A is 2 into 10 power minus 6, alpha B is 1 into 10 power minus 6. So this value is 2 into radius of B is 0.1 and radius of A is 0.2, 0.1 by 0.2 half square into the time it has taken is 2 hours. So this value becomes 2 by 1 by 4 into 2, 4 by 1 hour. So your answer here is 1 hour. This is transient heat conduction. This is beauty of Fourier number. This question, why ACE Academy has picked and given it in your score booster question is, such question comes, I'm for sure 1 in 100 will solve, and that one member should be from ACE Academy. This is the homework that the Academy always makes, and the question is having that particular depth. Then Convection. Nusselt number is some constant C, Reynolds power m, Prandtl power n represents heat transfer under forced convection. Say, if you are writing it, Nusselt number is some constant C into Grashof number into Prandtl number to the power of n. This is free convection. This is obtained from your Buckingham's pi theorem. So, Nusselt number is some constant C, Reynolds power A, Prandtl to the power of B, or m as well as n if you are writing it. This is your forced convection. This is your forced convection. Then let's go to another particular questions. The following figure was generated from experimental data relating to spectral blackbody emissive power radiation to wavelength at three temperatures T1, T2 and T3. The conclusion is that the measurements are wrong. Reason is this point. If you are looking at this, whenever temperature is decreased, because when T2 is less than T1, when temperature is decreased, the wavelength corresponding to the peak value should shift towards increasing wavelength. But here you are observing that it is moving. Earlier this was lambda T1 maximum. Now you are observing that it is shifting towards lower wavelength, lambda T2, and your lambda T3. Wrong. The point is lambda max into T should be constant equal to 2898 micron meter Kelvin. Wien's displacement law. When temperature is decreased, wavelength should increase. But it is not happening so. What is happening? You are observing that the wavelength is also decreasing with the decrease in temperature. Wrong. So, first correct because maximum EB lambda show the correct trend. Wrong. Correct because Planck's law is satisfied. Wrong. What Planck's law says? Planck's law says that energy is not radiated continuously but discontinuously. Energy packets called quanta or photon. Energy associated with the emitted photon or quanta is directly proportional to frequency of emitted radiation. And if you are going with the Planck's distribution law, EB lambda is equal to C1 lambda to the power of minus 5 by E to E power C2 by lambda T minus 1. It tells the trend that with decreasing temperature, wavelength should increase. That means your actual plots should be, if this is T1, the plot, if you are writing it for T2, say, it should be like this. This should be equal to your value of T2. So, it is not so. That is not the behavior which we have to obtain. So, display settings. Okay. Then I'll go to the next slide. I'll go to the next slide. I'll go to the next slide. Consider the radiative heat exchange inside an annulus consider the radiative heat exchange inside the annulus between two very long concentric cylinders. One minute, I'll just go. Yeah, we are here. Back live, no worries. Consider the radiative heat exchange inside an annulus between two very long concentric cylinders. Radius of outer cylinder is R0 and that of inner cylinder is Ri. The radiation view factor of outer cylinder onto itself is, say, whenever you are writing shape factors, these are emitters, I am writing here, two emitters and two receivers, and the sum of all shape factors should be equal to 1. Now, you are having two concentric cylinders. This is 1, this is Ri, this is R0. Then, if you are looking that this particular surface is 1 and this inner is 2, outer is inactive and this is inactive, 1 1 equal to 0, 1 on 2 equal to 1. And if you write your reciprocity theorem, you have A1 F1 on 2 is equal to A2 F2 on 1. You can calculate F2 on 1, A1 by A2 into F1 on 2, 2 pi R1L by 2 pi R2L. This becomes, if you are writing it, Ri by R0. So, this value is 1 minus Ri by R0. So, answer is D. Shape factors, when you are writing the shape factors. So, F11 equal to 0, F1 on 2 equal to 1, F21 is equal to Ri by R0, F22 is equal to 1 minus Ri by R0. Next. Because shape factors are always asked question. If you look at this question, the peak wavelength of radiation emitted by a black body at a temperature of 2000 Kelvin is 1.45 micron meters. If the peak wavelength of the emitted radiation changes to 2.9 micron meters, then the temperature of the black body is, this is lambda max into T is always constant for a black bodies, and he is not giving you wavelength at any other point, rather he is giving you peak wavelength, lambda max. So, I will write it as initially this is at 1.45 micron meters into 1000, no 2000 Kelvin. This is equal to, I will write lambda max into 1 into T1 is equal to lambda max 2 into T2. This is what I am writing it. So, this is 2.9 into T2. So, T2 is equal to 1.45 divided by 2.9 into 2000 comes out to be, this is half, 2000 by half is 1000 Kelvin. Wien's displacement law. I'm telling you, Wien's displacement law is such an important question. Like they may ask you anything. Say suppose if I ask you what is the lambda max corresponding to solar radiation, say solar radiation, then you have to write it as 2898 micron meters divided by 5700 Kelvin, approximately around 0.503 micron meters. There's only note, extra note, core boosting. Or if they ask you lambda max for earth radiation, say if they have asked, then this value is equal to 2898 divided by 300, approximately around 9.66 micron meters. This is infrared, IR. This is visible light. This is the reason why you see the sun. Else you might not have seen the sun with our naked eye. Then, let's go to this question. Now, this is a question where irradiation, radiosities, as well as gray body concepts come. A flat plate made of cast iron is exposed to solar flux. That means it is the irradiation that is coming from the sun, which is equal to 600 watt per meter square at an ambient temperature of 25 degrees centigrade. So T infinity is equal to 25 plus 273. My catch is, whenever you go into radiation, whenever he gives you temperature, first check the unit of temperature. If it is not in Kelvin, convert into Kelvin. If it is in Kelvin, well and good, keep it in the same way. So this is 298 Kelvin. Assume that the entire solar flux is absorbed by the plate. That means whatever radiation that is falling on the plate G, irradiation, which is equal to 600 watt per meter square, is completely absorbed. Okay. Now, cast iron has a low temperature absorptivity of 0.21. As per Kirchhoff's law, emissivity is equal to absorptivity. So, this is having 0.21. It's emissivity. Use Stephens-Boltzmann constant 5.669 into 10 power minus 8. Neglect all other modes of heat transfer. That means there is convection. So, it's asking you to neglect convective effects on the top surface of the plate. Under aforementioned conditions, radiation equilibrium temperature of the plate is. That means this is subjected to absorption and there is original surface emission. So, I will write this value as whatever the amount of heat that is being falling on it, all that is emitted, and as it is a gray body, it is epsilon times emissive power of a black surface, which is equal to sigma, and as this is per square meter, surface area is also 1 square meter, epsilon sigma into Ts power 4 minus T infinity power 4. And whatever the radiation that is emitted from the surface 1, everything is going into the ambience, hence the shape factor of this plate with respect to that particular ambient should be equal to 1. So, if I am writing this is 600 equal to 0.21 into 5.669 into 10 power minus 8 into Ts power 4 minus 298 to the power of 4. This should fetch you the temperature. And you round it up to the nearest integer and then give that total value. Suppose you got around 512.3 say, then write it as 513 Kelvin. So, temperature should be expressed in Kelvin and then subtract minus 273, because it's asking you in degree centigrade. Whatever temperature you are getting it, Ts minus 273 will give you the temperature surface in degrees centigrade. That's the answer. Equilibriums. Everywhere they are asking you equilibriums. Then let's go to the next question. A solid cylinder is located at center of a hollow sphere. So there is a sphere, and at the center there is a cylinder. So if you look in other view, this is your this is what you have. Slightly moved it, not exact, it's side view. The diameter of the sphere is 1 meter. So this diameter of this particular sphere is 1 meter, while cylinder has a diameter and length of 0.5 meters. So its diameter is 0.5 and length is 0.5 meters. And dia is also 0.5 meters. The radiation configuration factor F11 is, now solid cylinder surface is 2, this surface is 2 and sphere is 1, that is what he is saying. So if you are trying to write the shape factors, emitting and receivers, 2 receivers, 2 emitters, as it is an enclosure, sum of all shape factors should be equal to 1. This is my shape factor matrix which I am trying to write. Now 2 is the inside cylinder which is convex and it has 2 faces which are clearly plane walls, hence 2 is 0. 2 with respect to 2, not this. Hey, come on. Just a minute. I will. This is 2 equal to 0. 2 on 1 is 1. And I know A1 F1 on 2 is equal to A2 F2 on 1. He has just confused. In regular class, we would be taking inside is 1, but now he has given inside is 2, outer is 1. So I am trying to come in this other way. So area is 4 pi, radius is 0.5 square into F1 on 2 is equal to A2 is its lateral surface area pi dl plus 2 pi r square. So I will write it as 2 into pi by 4 d square. This is for your cylinder into shape factor is 1. So I will be getting F1 on 2. So this value is pi and pi get cancelled. This is 4 into 0.25 into F1 on 2 is equal to diameter is 0.5 into 0.5 plus 2 into this value is 0.25 into 0.25 divided by 4. So finally when you are writing it, this value becomes 0.375, this value becomes 0.625. Answer is 0.625. Then let's go into a question of heat exchangers. I picked a question of heat exchanger wherein I am using a condenser. In a condenser of a power plant, the steam condenses at a temperature of 60 degrees centigrade condensation is isothermal heat rejection. So temperature here is 60 degrees and here is also 60 degrees centigrade. Cooling water enters at 30 degrees and leaves at 45. 30, 45. LMTD, this is delta T1, this is delta T2, difference. So LMTD is equal to delta T1 minus delta T2 by log delta T1 by delta T2. This value is 30 minus 15 by log 2. 15 divided by 0.693. Answer should be maybe around 21.6. I don't know. Let's not jump to conclusion. So calculate that particular value. Answer is 15 divided by 0.693, around 0.7. So 150 by 7. So this should be around 21.6. Next, in a certain heat exchanger, both the fluids have identical mass flow rate, specific heat product. That means m dot into C is constant. Hot fluid enters at 76 degrees centigrade, leaves at 47. 76, 47. And cold fluid enters at 28, leaves at 55. See, outlet temperature of cold fluid is more than the outlet temperature of hot fluid. So this should be a counterflow heat exchanger. So this enters at 28, leaves at 55. Effectiveness of the heat exchanger is, whenever he is asking you effectiveness, either it is hot fluid, because it is totally dependent on the product of mass flow rate into heat capacity. M dot HCH is less than M dot CCC, then it is based on hot fluid. If M dot CCC is less than M dot HCH, it is dependent on cold fluid. But when both of them are same, it can be on either one. But if you make an energy balance, it will not set so. Reason is, if you check 76 minus 47, you should, the value is 9 and you should get 29 degrees centigrade. If you look at temperature drop for cold fluid, it is 55 minus 28. And if you are subtracting it, you are getting 27 degrees centigrade because heat exchanger is fouled. So what I will do is, first I will calculate as per hot fluid, it is THI minus TH naught divided by THI minus TCI. This value comes out to be, hot fluid is 76 minus 47 divided by 76 minus 28. This is approximately around 0.6. If you are writing it based on cold fluid, you will be getting it as 55 minus 28 divided by 76 minus 28, approximately around 0.56. If you take average of these two, you will be getting around 0.58 is answer. Energy balance has failed because heat exchanger is fouled. You will be getting two values, 0.6 or you are getting around 0.6 or 0.56. But it is not so. Both of them should be same when the mass flow rate into specific heat is constant. but heat exchanger is fouled. Under such situations, calculate both on hot fluid basis, both on cold fluid basis, take an average, answer should be 0.58. Then hot oil is cooled from 80 degrees centigrade to 50 degrees centigrade in an oil cooler which uses air as the coolant. So, this is 80 degrees to 50 degrees. Air temperature rises from 30 to 40. So, here cold fluid outlet temperature is less than hot fluid outlet temperature. It can be parallel flow, it can be counter flow, it can be cross flow, anything it can happen. If cold fluid outlet temperature is greater than hot fluid outlet temperature, then it will be counter flow heat exchangers. So, first what I will do, I will take parallel flow configuration. This is 30 degrees centigrade and this is 40 degrees centigrade. Because he is saying that the designer uses a LMTD value of 26. So, first let us take parallel flow, calculate LMTD of parallel flow. This comes out to be 50 minus 30, 50, 80 minus 30, 50 minus 50 minus 40, 10 divided by log 5. This is 40 by log 5. This value is less than 26. If you want, you check. Then, if you take it as a counter flow heat exchanger, 80, 50, 30 and 40, and if you are calculating LMTD of counter flow heat exchanger, 80 minus 40, 40, 50 minus 30, 20 by log 2, 20 by log 2. This value is greater than, because 20 divided by 0.693. This value is greater than 26 degrees centigrade. So, whatever the value that you are calculating as a parallel flow, you are getting around 24 degrees centigrade here, counter flow around 28 if you want to check it. But you are getting a value between parallel and counter, answer should be cross flow. As LMTD value obtained is less than counter flow, greater than parallel flow, it should be cross flow. Cross flow heat exchanger. See the pick of the questions in the score booster, it is not regular. These are the questions where your known concepts with the logic and the subjectual concepts are imbibed at every point. At every point, you are trying to give it. Then, an industrial gas enters a parallel flow heat exchanger at 250 degrees centigrade. THI is 250 degrees centigrade. With a flow rate of 2 kg, m dot h is 2 kg per second. To heat water stream, water having specific heat 4 kilojoule per kg enters the heat exchanger TCI at 50 degrees centigrade with a flow rate of 1 kg per second. M dot C is 1 kg per second. Heat exchanger has an effectiveness of 0.75. Effectiveness is 0.75. The gas stream exit temperature is, first what you do, write m dot h into CH. This value is 2 into 1. So, it is 2 kilowatt per Kelvin. And you write m dot CCC. If you write water, this value is 1 into 4. So, this is 4 kilowatt per Kelvin. As m dot HCH is less than m dot c cc. Effectiveness is based on hot fluid, which is Thi minus Tho divided by Thi minus Tci. So, you are getting 0.75 is equal to hot fluid inlet temperature is Thi 250 minus Tho. The gas stream exit temperature will be divided by 250 minus 50. So, you will be getting Th naught is equal to 0.75 into 200, 150, and this value plus 250. So, 250 minus 150, answer is 100 degrees centigrade. Gas stream exit temperature is 100 degrees centigrade. So, dear friends, if you have observed these things, every problem has a very meticulous concept wherein whomsoever tries to attempt these particular questions, definitely your ranks will boost. This is definitely a score booster question. All the best. Please follow them. I wish in this new year 2026, those who are following ACE Academy score booster session will get All India rank 1. All the best. Bye. Thank you.